Okay, assalamu alaikum. So today I'm going to explain you advanced material synthesis by atom transfer radical polymerization. So how advanced material can be synthesized using different polymerization technique. The content of the today presentation is reversible deactivation radical polymerization or controlled radical polymerization methods. So all of the topic or the subtopic included in this main topic, that is reverse ATRP, simultaneous reverse and normal ATRP or AGT ATRP. It can also be named as simultaneous reverse and normal initiation process. And the second subtopic is activator regenerated by electron transfer or ARGET ATRP, initiation for continuous activator regeneration ICAR, and we have to also compare supplementary activator radical addition ATRP with the single electron transfer leaving radical polymerization. This we have to also address the electrochemical ATRP, where ATRP is initiated or the polymerization is carried out in the presence of applied potential current or charge. Similarly, we can also initiate polymerization by using light as a source of radical initiation. Now, just comparing the normal and reverse ATRP, we already talked about normal ATRP, in which alkyl halide initiator react with the transition metal in lower oxidation state. This is the normal ATRP, in which the transition metal complex in lower oxidation state react with the initiator, and it initiate the polymerization by producing this free radical initiator and react with the monomer and make a propagated chain, and the metal is converted to higher oxidation state. Similarly, what happen actually in reverse ATRP? So everything reverse, because this is initiated by the addition of transition metal in higher oxidation state and to a free radical. So this free radical is added to this higher oxidation state, and we have in this reverse direction. This is the transition metal complex in higher oxidation state. To this the initiator is added, either this is alkyl halide initiator or a normal initiator by decomposition of the initiator species. So a free radical is added to the higher oxidation state metal complex, and this is converted into activated complex. This activated complex then react with the monomer or the dormant polymer chain, and it initiate the polymerization. By addition of more monomer, we have propagation, and the activator is converted into higher oxidation state. This is also named as simultaneous reverse and normal initiation. So initiation is normal, but we have a reverse also to produce the activator. Another one we already talked briefly, the AGT ATRP, that is activator generated by electron transfer ATRP. This simultaneous reverse and normal initiation evolved into another area, that is activator generated by electron transfer, where only ATRP initiator added to higher oxidation metal complex, which produces activator by addition of reducing agent. So reducing agent either may be a chemical species, that is organic, ascorbic acid, or metal wires such as copper in the zero oxidation state. This higher oxidation state metal complex is added with this red color reducing agent, and it is creating an activator. This activator react with the ATRP initiator alkyl halide or a dormant monomer chain, polymer chain. So we have this initiation. Initiator is free radical is created, this combined with monomer, and we have a growing polymer chain, and deactivator is generated. This deactivator can again react with the reducing agent. We have another important type of ATRP, that is activator regenerated by electron transfer ATRP, which is a green procedure because it is green approach because it uses ppm level of a catalyst in the presence of appropriate reducing agent. This is a new way to carry out reversible deactivation radical polymerization. This process uses a repetitive reduction oxidation cycle between the reducing agent and a transition metal catalyst in a higher oxidation state. So it consume all oxygen in the reactor. It uses equimolar amount of ligand and copper. Is low level of catalyst is 6 ppm or in ppm range. The ascorbic acid is used as a reducing agent, or metal wire can also be used as a reducing agent. So here this deactivator is activated by adding a suitable reducing agent, and we have activator generated here. This activator carried out the polymerization by producing this free radical. So the terminated polymer chain either consists of this double bond, or it is reduced, or it is some kind of addition termination reaction. So the polymer is produced by terminated reaction. There are several advantages of this kind of polymerization, that the side reactions are eliminated. We have higher conversion, and we can also prepare copolymers with the higher molecular weight and retaining the chain and functionality. So at the end we have functional group, we can modify the polymer. So this is some kind, because with the help of this we can prepare copolymer also. Another one is initiator for continuous activator regeneration, or ICAR, that is considered as reverse ARGAT-ATRP. So part of the mechanism you can look the reverse ARGAT-ATRP. What will happen in this case? Here a source of organic free radical is implied for the continuous regeneration of low level of the activator. So free radical is added, and this can generate this activator when it reacts with the higher oxidation state transition metal complex. Reaction is driven to completion with low concentration of added free radicals, and the polymerization rate totally depend on the decomposition of this, or the production of this free radical. For the mechanism you can see the reverse of ARGAT-ATRP. Another important topic which we have to compare and fully explain, that is comparison of supplemental activator and reducing agent, that is SARA ATRP with the single electron transfer laying radical polymerization. So these are very critical comments between different scientists were these two mechanism of polymerization. So in the first case, that is SARA ATRP, the metal wire is used, or the copper in the zero oxidation state, undergoing comproportionation reaction with the Cu. So I would like to tell you, you can look by yourself also. Comproportionation reaction are those reaction in which a species in two different oxidation state produces a species or two species in the same oxidation state. So in this copper in the zero oxidation state combined with the copper in the +2 oxidation state, they produce two copper in +1 oxidation state, and this process is called comproportionation reaction. In this way we have this activator generated, and this activator then carry out polymerization. Later on I will show you in the mechanism. Similarly, this copper in zero oxidation state rarely can react with the alkyl halide, but this is rarely. Later on we have to explain this to create the activator, although the majority of alkyl halide is activated by copper in the +1 oxidation state, and this is through by comproportionation or deactivation with CO. Next is the comparative topic is single electron transfer leaving radical polymerization, that is SET-LRP. This is a kind of ATRP in the presence of this. This is responsible for the activation in mostly in polar organic solvent. So activation is done of alkyl halide by copper wire, or copper is applied in the powder state, wire state, or mesh, or different kinds, via outer sphere electron transfer to form the radical anion. So I have to explain you what is meant by outer sphere electron transfer, because two mechanisms are used. One is outer sphere electron transfer, another one is inner sphere electron transfer to form the radical anions. This is done by disproportionation reaction of CO species. So disproportionation reaction in which a species is oxidized and reduced. So on one side this is reduced to copper in zero oxidation state, and another side this species copper in +1 oxidation state is oxidized to +2 oxidation state. So that's why this is called disproportionation reaction, in which a species is undergoing a redox process. A same species are undergoing a redox process, that is oxidized and reduced. So this is the mechanism of SARA ATRP. You can see carefully, because this is very important. The bold line or the solid line indicate the major reactions. So in this case the green color, if you see closely, the green color is for comproportionation reaction, in which a species in different oxidation state produce a same oxidation state, that is copper in +2 oxidation state, and zero oxidation state is coming to +1 oxidation state, and this is carrying out the main activation, that is alkyl halide or this dormant polymer chain. This produce this free radical, and this later in other step carry out the propagation of the polymer chain, and this is converted to deactivator. So this is the main activator. You can see here activation is also done by this copper wire, copper in zero oxidation state, but this is minor, and these similarly this deactivation is also major. But you can see the disproportionation is shown by this dash line, which is the minor contribution, that is species, the same species is converted to different oxidation states. So this is some kind of equilibrium between. Now you can see the single electron transfer leaving radical polymerization, in which a same species, that is copper in +1 oxidation state, is going to reducing, that is going to copper in zero oxidation state. At the same time it is going to copper in +2 oxidation state. So you can see that the major contribution reaction activation is done by activation is done by copper in zero oxidation state, which produce the free radical, and activation by copper in +1 oxidation state is shown as minor, it is almost negligible, it can be neglected, and the major mechanism in this case is disproportionation, that is shown in blue line, and comproportionation is minor. So this is the main difference. The outer sphere and inner sphere. So this is the inner sphere, so the species which is inside. So SARA is actually concerned with the or focusing on the inner sphere electron transfer, but SET-LRP is focusing on the outer sphere, that is the species which is outside the reaction, that is at the extreme end, and they are actually the major contributor for this reaction. So that's why it is called outer sphere. This is explanation, you can see by yourself, I already explained this. So this is just the comparison that the copper in the zero oxidation state, this is active, carry out this, and it is converted into free radical is generated. So this is the comparison of activation rate constant of copper in 1 oxidation state to 0 oxidation state. So this rate constant is given here, this is stainless 2, and this reaction is carried out in demeso and water for comparison. Similarly, this copper is carrying out this activation by production of free radical and is converted. So the rate constant you can see here, activation disproportion, so this is quite higher in this case. So now this is just a very conclusive remarks. Critics, experimental data disagree with the single electron transfer leaving radical polymerization and confirm that the mechanism, that is this supplemental activator and reducing agent ATRP is confirmed. So activation, the conclusion is that activation step involve inner sphere electron transfer, that is the activation by copper in plus 1 oxidation state, rather than outer sphere electron transfer. That outer sphere electron transfer I have already shown that at the extreme end, that was the copper in the 0 oxidation state and the plus 2 oxidation state. So the inner sphere is just inside the reaction intermediate, that is some side inside, that is plus 1 oxidation state, and alkyl halide is predominantly activated by copper species in plus 1 oxidation state and not by copper in 0 oxidation state. So this is the conclusion. Organic solvent, now you can compare in the solvent. So if you are carrying out reaction in organic solvent, that is non-polar solvent, so comproportionation is faster than disproportionation. That is activation by copper plus 1 oxidation is much faster if we have organic solvent, but if we have a polar solvent, then we have comproportionation. If we have a polar solvent, then we have a disproportionation. Now the important topic is electrochemical ATRP. So there are several drawbacks of chemical reducing agent, that they are producing toxic chemical, or they are leaving behind oxidized byproduct in the reaction mixture. So for that reason we are carrying out electrochemical methods using applied current or potential or charge sparse to control the polymerization rate. In this case, for this purpose, cyclic voltammetry is a very popular technique is applied, in which applied potential applied electrode potential defines or control the ratio of the copper in the oxidized in the reduced state, that is in the activated state, and in the oxidized or inactive state, or in the higher oxidation state. So this ratio is controlled by varying the applied potential. So in this way we can produce activator and initiate the polymerization. So it is stated, it is already studied or confirmed experimentally that a more negative applied potential induces a faster reduction resulting in faster polymerization because this is providing electron, and this is converting this oxidized to this reduced species, that is activator. So you can see here a note, here is the activator and here is the deactivator. So activator is produced when electron is supplied to this deactivator. So this is anodic current, this is cathodic current. So if you apply more negative potential, so electron is supplied to this deactivator, is converted to activator, and this activator then initiate the polymerization by producing the free radical, and free radical add to the monomer, propagation is carried out, and we have also termination in the same way. Another important last topic, subtopic we have to focus here, that is Photo-ATRP. In Photo-ATRP, light is used to carry out polymerization or control the polymerization. In this case, an experiment is done in which methacrylic monomer with ppm level of copper catalyst is used without using any photo initiator, and a successful polymerization is carried out. This can have good control over polymerization reaction, and the polymerization can be stopped or reinitiated by just simply switching on and off the light from the radiation source. This can be carried out in organic solvents and as well as in water. This is the mechanism in which we have this deactivator, and when we supply or radiate this deactivator, so deactivator is reduced in the presence of this ligand, that is trialkyl amine. So we have this activator generated. This activator then initiate the polymerization by producing free radical, and we have this propagation. Similarly, yes, so monomer are added and we have this propagation, and deactivator is generated. So this is on off light, so we can control the polymerization. Light continuously reform the activator, allowing control over the rate of reaction on demand by switching on and off the light from the source. So this is also environmental friendly polymerization. Hope that clarify the topic, which is the preparation of advanced material using atom transfer radical polymerization.